Welcome to the deep dive. We all interact with computers every single day, but have you ever stopped to think about the fundamental machinery that, well, makes it all happen?
Probably not often enough.
Exactly. So today, we're going to pull back the curtain and really dig into computer organization and architecture.
Mhm.
Think of this as your essential guide to understanding the core building blocks and how they work together, almost like prepping for a test on the inner workings of your digital world.
That's a good way to put it. We're using COA mod1.pdf as our main source here, basically unpacking the essential elements of a computer.
Right.
Our mission is to move beyond just knowing what a computer does and truly grasp how it does it,
Yeah.
at a foundational level.
So by the end of this, listeners should have a much clearer picture.
That's the goal.
Yeah.
A clear picture of the principles that govern, well, all computing, really.
Okay, let's get into it. Our source material starts by identifying 5 fundamental functional units in every computer system. These are the big players, each with a crucial role.
That's right. The core building blocks.
And we're talking about the input unit, the arithmetic logical unit, or ALU,
Yep, the ALU.
the control unit, the memory unit, and the output unit. Let's maybe take them one by one, really nail down what each one does.
Excellent idea. Let's start with the input unit. Makes sense to start there.
The way stuff gets in.
Exactly. This is the gateway through which data and programs enter the computer. You're already familiar with devices like, keyboards, mice, scanners.
The usual suspects.
Right. But what's crucial to understand is that the input unit isn't just passively receiving information. It performs a vital translation.
Ah, okay. Translation how?
Well, it converts real-world data, like the physical movement of your mouse or the light patterns from a scanned image, into electronic signals the computer can actually process.
So it digitizes it.
Essentially, yes.
Mm-hmm.
This often involves analog to digital conversion, or ADC. It's that critical first step,
Yeah.
making external info understandable to the digital realm inside.
That makes perfect sense. So the input unit is like the computer's senses. Okay. Now the output unit, that's how the computer communicates its results back to us, right?
Precisely.
We're talking about monitors, printers, speakers, that sort of thing.
Exactly. The output unit takes those processed electronic signals from the computer and transforms them back into a form that we humans can understand.
So the reverse of the input process.
Pretty much. This often involves digital to analog conversion, or DAC. So the binary code that the computer manipulates gets turned back into visual displays, printed text, or audible sounds. It's the bridge from the digital world back to our analog world.
Got it. Input to get information in, output to show us the results. Clear enough. Now, the memory unit, this must be where all the data and instructions hang out.
You're absolutely right. The memory unit is where the computer holds the data it's currently working on, plus the instructions telling it what to do next.
And our source emphasizes it's not just one big storage bin.
Right, it's organized hierarchically. At the top, you've got primary storage, which is your random access memory, or RAM.
The fast.
Very fast memory, yeah. The processor can access it super quickly. It holds the data and applications that are currently active. Think of it as the computer's workspace, or like its short-term memory. Things need to be readily available there.
Okay, so RAM is for what's being actively used right now. What about everything else? Our files, programs we're not running, that's where secondary storage comes in, like hard drives or SSDs.
Exactly. Secondary storage provides long-term, non-volatile storage. Non-volatile meaning it stays there even when the power's off.
Right.
Think hard disk drives, solid-state drives. Optical media back in the day, it's much larger capacity, but generally slower than RAM.
So like the computer's filing cabinet or long-term memory.
A good analogy. The key here is understanding this layered approach. Faster, smaller primary memory for active tasks, and larger, slower secondary memory for persistent storage. This hierarchy is absolutely crucial for balancing speed and capacity.
That distinction is very clear now. All right, next up, the Arithmetic Logical Unit, the ALU. This sounds like the workhorse of the computer, where the actual processing happens.
That's a great way to put it.
Yeah.
The ALU is the component responsible for performing all the arithmetic operations: addition, subtraction, multiplication, division.
The math stuff.
Yeah, the math stuff. And also the logical operations like AND, or not T, and comparisons like, is this number greater than that one?
Okay.
So when the computer needs to do a calculation or make a decision based on data, that data gets brought from the memory unit or maybe registers to the ALU.
Right.
The ALU does its thing, performs the operation, and the result is often sent back to the memory unit or a register for storage or further use. All the data manipulation fundamentally happens within the ALU.
So the ALU does the number crunching and the logical checks. What then is the role of the control unit? It sounds like it's orchestrating everything.
Your intuition is spot on. The control unit acts like the brain's conductor, maybe?
Yeah.
The central coordinator for the entire system. Its main job is to manage and synchronize the activities of all the other functional units. It does this by figuring out the sequence for executing instructions.
How does it do that?
Well, it fetches an instruction from memory, decodes it, figures out what needs to be done, and then issues a series of control signals to the other units.
Telling them what to do.
Exactly. Telling the memory unit when to read or write data, telling the ALU which operation to perform, telling the I/O units when to transfer data. It ensures everyone works together correctly to execute a program. It's basically the director of the whole show.
Okay, so we have our 5 main units, each with a distinct, vital role. Input, output, memory, ALU, and the control unit directing them. Now, how do they actually collaborate to run a program?
Right, this is where we get into the basic operational concepts. A program at its core is just a sequence of instructions stored in the memory unit.
A list of commands.
Pretty much. To execute this program, the processor, which essentially combines the ALU and the control unit, fetches these instructions from memory, one after another, and performs the operations they specify.
And our source gives examples like moving data or doing math.
Yes, moving data between memory and registers, or performing arithmetic on data held in registers.
Registers, right. We touched on those. They're like the processor's own super fast scratch pads.
Exactly. Registers are small, very fast storage locations built right into the processor.
Yeah.
They hold data the processor is actively working on right now, operands for calculations, memory addresses, that kind of thing.
Well, okay.
Now let's trace the execution of just one instruction. It all starts with a program counter, or PC.
The PC.
The PC is a special register. It holds the memory address of the next instruction that needs to be executed. Think of it as a bookmark, pointing to the current step in the program.
Okay, so the PC knows what's coming up. What happens next?
So the address that's in the PC gets transferred to another special register, the memory address register, or MER.
MER, got it.
The MER holds the specific memory location the processor wants to access right now. Once the MER has the address, the control unit sends a read signal to the memory unit.
Knocks on memory's door, basically.
Kind of, yeah. In response, the memory unit fetches the instructions stored at that address and sends it back to the processor, placing it in the memory data register, or MDR.
MDR, another temporary spot.
Exactly. The MDR acts as a temporary buffer, holding data being transferred between the processor and memory in either direction.
Okay. PC points to address goes to MER, instruction comes back via MDR. What's the next step?
The instruction that's now sitting in the MDR is then moved into the instruction register, or IR.
IR. Okay, so the instruction lands there.
Right. The IR holds the instruction that is currently being decoded and executed.
Yeah.
The control unit examines the instruction in the IR to figure out what operation needs to be done and what operands the data are required.
And if it needs data from memory?
If the instruction needs data from memory, the addresses of those operands are sent to the MAR. Another read happens. The operands come back into the MDR.
Okay.
And often they get moved into general-purpose registers within the processor. These are often named R0, R1, R2, and so on. They hold the data the ALU will actually work with.
So gather all the needed ingredients, the data, into these general-purpose registers.
Yeah.
And then the ALU finally does its thing.
Precisely. The ALU takes the operands from the registers, performs the operation specified by the instruction, like add or compare, and the result is typically stored back into one of those general-purpose registers.
Or sometimes back to memory.
Or sometimes back to memory, yes.
Yeah.
If the instruction is meant to write a result back to memory, the destination memory address goes in the MAR, the data to be written from a register usually goes in the MBR, and a write signal is sent to the memory unit.
Okay. And crucially, what happens to the PC, the program counter, during all this?
Ah, yes. Crucially, after an instruction is fetched, the program counter, PC, is incremented. It gets updated to point to the next instruction in sequence in memory.
So it's ready for the next cycle.
Exactly. This ensures the program executes step by step, unless, of course, a special instruction like a branch tells it to jump somewhere else. We'll get to that.
That's a detailed breakdown, but yeah, it really clarifies the flow. Fetch, decode, execute, and get ready for the next one. Now, our source also mentions interrupts. What are those about?
Interrupts. Think of them as a way for other parts of the computer system to get the processor's immediate attention.
Like raising a hand?
Sort of.
Yeah.
For example, when you press a key, or when your network card gets some data, These devices need to tell the processor, hey, something important happened, deal with me now.
Okay.
They do this by sending an interrupt signal to the processor. When the processor gets an interrupt, it usually finishes the current instruction it's working on, then temporarily suspends the program it was running.
Puts it on pause.
Exactly. It saves its current state and jumps to a special piece of code called an interrupt service routine. This routine is specifically designed to handle whatever caused the interrupt, read the keystroke, process the network packet, etc.
And then,
Once the interrupt service routine finishes its job, the processor usually restores the state of the program it paused and resumes executing it right where it left off.
like pausing a movie to answer the door, then hitting play again?
That's a great analogy for it. It allows the system to be responsive to external events without constantly checking every device.
Okay, makes sense. So how do all these different units, processor, memory, I/O devices, actually connect and talk to each other? That's where buses come in, right?
Exactly. A bus is basically a shared communication pathway. Think of it like a highway system.
A highway for data.
Yeah, a collection of wires or electrical pathways used for transferring data between the different components. Our source describes a simple single-bus structure first.
One main road everyone shares.
Pretty much. Imagine one shared highway that the processor, memory, and I/O devices all use to send and receive information. This bus typically consists of three main parts, three sets of lines.
Which are?
Address lines, data lines, and control lines.
Okay, so address lines specify where the data is going or coming from.
Right, like the destination address on a package.
Data lines carry the actual information being transferred.
Yep, the contents of the package.
And control lines manage the whole process, like traffic signals.
You've got it precisely. They manage the timing, indicate whether it's a read or write operation, things like that.
So how do all the different devices connect to this one shared bus, especially I/O devices?
Input-output devices connect through special circuits called interfaces, or controllers. Each I/O device interface has a unique address, or maybe a set of addresses, tied to its internal registers.
It's like its own specific exit ramp and mailbox.
Kinda, yeah. When the processor wants to talk to a specific device, say the keyboard interface, it puts that device's address onto the address lines of the bus. All the devices connected to the bus are listening, basically monitoring these address lines. The one device that recognizes its own address then pays attention to the control signals from the processor on the control lines, like a read command to get data from the device or a write command to send data to it.
And the actual data travels on the data lines?
Exactly. The data transfer then happens over the data lines between the processor and that specific device interface.
And our source mentioned something called memory mapped I/O. That sounds efficient.
It is. It's quite clever. In memory mapped I/O, the system treats the I/O device registers as if they were just regular memory locations.
So they share the same address space.
Exactly. The address space for main memory and the address space for I/O devices are unified. This means the processor can use the very same instructions to access both memory locations and the registers inside I/O device interfaces.
Oh, okay. So you don't need special I/O instructions.
Oh, right. For example, an instruction normally used to load a value from a memory address, like load R2 address, could also be used to read data from, say, the keyboard's input data register, if that register has been assigned a specific memory address.
So load R2 keyboard data address would work just like reading from RAM.
Precisely. And similarly, a store instruction used to write to memory could send data to an output device like store R2 display data address.
That does simplify programming. No need for a separate set of I/O commands.
Exactly. It streamlines things. Now, for this to work, each I/O device interface needs a few key parts.
Like what?
Our source mentions an address decoder. That's the circuit that recognizes the device's unique address when it appears on the address bus. It also needs data and status registers.
Data register for the info being transferred, status register for what?
Status register holds information about the device's current state, like is the keyboard ready with a new character, is the printer busy or ready for more data, that kind of thing. And finally, it needs control circuitry to actually manage the data transfer and respond to those control signals from the processor.
Okay, buses are the highways, interfaces are the on-off ramps with specific addresses. Now let's zoom in on the memory unit itself. How is it structured internally with locations and addresses?
Right, so fundamentally, the memory unit is made up of a huge number of individual storage cells. Each cell holds a single binary digit, a bit 0 or a 1.
The basic unit.
The very basic unit. These bits are then grouped together into larger units. A key one is the word.
Oh, word.
Yeah, a word is a group of a fixed number of bits that the processor often handles together as a single entity. The number of bits in a word is called the word length.
And that varies.
It does. Modern computers typically have word lengths like 16, 32, or 64 bits. Another absolutely crucial unit is the byte, which is universally defined as 8 bits.
8 bits to a byte. Got it.
Now, to access any specific piece of info in memory, whether it's a whole word or just a single byte, each storage location gets a unique identifier, its address.
Like a house number on a street.
Exactly like that. If a memory system uses, say, k bits for its addresses, it can uniquely identify up to 2 to the power of k different memory locations. That total range of addressable locations is called the address space.
Okay, every location has a unique address. But you said a word is made up of multiple bytes. How do we pinpoint individual bytes within a word, or just bytes in general?
That brings us to byte addressability. Most modern computers use byte addressable memory, meaning each individual byte in memory has its own unique address. So the very first byte might be address 0, the next byte address 1, then 2, and so on sequentially.
Okay.
Now let's say you have a computer with a 32-bit word length. That's 4 bytes per word, right? Since 32 equals 4.
Right.
In a byte addressable system, the first word would occupy the bytes at addresses 0, 1, 2, and 3. The next word would start at address 4 and occupy bytes 4, 5, 6, and 7, and so on.
So the address of a word is typically the address of its first byte, and word addresses are multiples of the word's size in bytes.
You got it. For a 32-bit, 4-byte word system, word addresses would typically be 0, 4, 8, 12, multiples of 4.
Okay, that makes sense. Now, our source mentions big endian and little endian. What are those about? Sounds like breakfast orders.
Yeah, the names are a bit quirky. They refer to the convention used for storing the individual bytes of a multi-byte word within those sequential memory addresses.
Okay, the order of the bytes within the word.
Exactly. In a big endian system, the most significant byte, the byte containing the highest order bits, the big end, is stored at the lowest memory address assigned to that word. The less significant bytes follow in increasing addresses.
Big end first at the start address.
Right. Conversely, in a little endian system, it's the least significant byte, the little n, that's stored at the lowest memory address. The more significant bytes follow it at higher addresses.
Little n first. Okay. Does it matter which one is used?
Well, within a single system, it doesn't really matter as long as it's consistent. But it becomes important when you transfer data between systems that use different endian conventions. You might need to swap the byte order for the data to be interpreted correctly.
Okay. A potential compatibility issue? What about word alignment?
Word alignment is about efficiency. It refers to the idea, or sometimes a requirement, that multi-byte data items, like words, should ideally be stored in memory, starting at an address that is a multiple of the data item size in bytes.
Why?
Because processors are often designed to fetch data in word-sized chunks most efficiently from addresses that align with word boundaries. For example, on a 32-bit 4-byte system, accessing a 4-byte word is usually fastest if that word starts at address 0, 4, 8, etc.
And if it's not aligned, like starting at address 1?
If a word is misaligned, say a 4-byte word starting at address 1, so it spans bytes 1, 2, 3, and 4, the processor might have to perform 2 separate memory accesses to fetch the whole word, one for bytes 0, 3, another for 4, 7, then extracting the needed parts. This takes extra time and complexity.
So alignment helps the hardware access memory more efficiently.
Got it. Now, when we access data, do we always use word addresses or sometimes byte addresses?
You use the address appropriate for the data size you need. When the processor needs a full word, like say an integer number, it typically uses the word's starting address, which should ideally be aligned.
Okay.
But when it needs just a single character, which is usually 1 byte, it will use the specific byte address of that character. The memory system is designed to handle both types of access.
Makes sense. Use the right tool for the job. Okay, that covers memory organization. What are the basic operations we can perform on this memory?
Fundamentally, there are just 2 basic operations, read and write.
Simple enough? Tell me about read.
The read operation retrieves a copy of the data stored at a specific memory location and brings it to the processor. Importantly, reading is non-destructive. The content of the memory location itself doesn't change after you read it.
Like photocopying a page. Exactly. To do a read, the processor sends the address of the location it wants to the memory unit, along with a read control signal. The memory unit finds that location and sends the data stored there back to the processor.
Okay. And the write operation. That must be how we put new information into memory.
Precisely. The write operation transfers data from the processor to a specific memory location. This operation is destructive.
Meaning?
Meaning whatever data was previously stored at that memory location gets overwritten, replaced by the new data being written.
Okay, it changes the memory content.
Yes. To do a write, the processor sends both the address of the target location and the data to be written to the memory unit, along with a write control signal. The memory unit then stores that data at that address.
Read to fetch, write to store, the two fundamental memory actions. Okay, let's move on to instructions themselves. Our source mentions 4 basic types of operations a computer needs to do. Let's focus on data transfers and arithmetic logic ops first.
Right. And to talk about instructions clearly, we need a way to represent them. Our source introduces register transfer notation, or RTN.
RTM. What's that?
It's a symbolic shorthand for describing data movement between registers inside the processor or between registers and memory.
Like a formula.
Kind of.
Yeah.
For example, R1 LOC means the content of the memory location named LOC is transferred into processor register R1. The square brackets often mean content of.
Okay, and the arrow shows the direction.
Exactly. The value on the right moves to the destination on the left. Another example, R3 R1 plus R2 means add the content of register R1 to the content of register R2 and store the result in register R3.
Simple and clear notation. And then there's assembly language. That's more like programming.
Yes, assembly language is a step up from the raw machine code, using human-readable mnemonic codes for instructions. It's closer to how programmers might interact at a low level.
So how would those RTN examples look in assembly?
Well, R1 LOC might be written as something like move LOC R1. The move is the operation code, the mnemonic. LOC is the source operand, R1 is the destination.
Okay.
And R3 U R1 plus R2 could be add R1, R2, R3. Add is the opcode, R1 and R2 are source operands, R3 is the destination. The exact syntax varies between different processor architectures, though.
Got it. Now, our source also describes instruction types based on the number of addresses they specify. 3 address, 2 address, 1 address. What's the difference there?
It's about how many operands, sources, and the destination are explicitly included within a single instruction.
Okay. Tell me about 3 address.
A 3-address instruction typically specifies 2 source locations and 1 destination location, like our add A, B, C example earlier, which means C gets the result of A plus B, C A plus B.
Makes sense. 2 sources, 1 destination. What about 2 address?
A 2-address instruction usually uses 1 address as both a source and the destination. For instance, add A, B might mean add the content of A to the content of B and store the result back into B. So B, A plus B.
Ah, so it overwrites one of the sources.
Often, yes. This can save instruction space, but if you needed to keep the original value of B, you'd have to first copy it somewhere else using a move instruction, like move B, C, then add A, C.
Okay, a potential extra step. And 1 address.
1-address instructions typically rely on an implicit special register, often called the accumulator. An instruction like add A would mean add the content of memory location A to whatever is currently in the accumulator and store the result back in the accumulator. So at AC plus A. You also need instructions like load A, ACEA, and store A to get data into and out of the accumulator.
So fewer addresses specified, but maybe more instructions overall for a task?
Potentially, yes. Different architectures make different trade-offs between instruction complexity and the number of instructions needed.
Okay, varying ways to structure instructions. Now, how are these instructions actually executed one after another to get something done?
All right, this brings us to instruction execution and what's called straight-line sequencing. Imagine your program is just a list of instructions stored in consecutive memory locations, address I, then I plus 4, I plus 8, and so on, assuming 4-byte
A
instructions.
simple sequence.
Exactly. The processor starts by fetching the first instruction, the one at address I, whose address is in the program counter, PC. It executes that instruction. Then, crucially, the PC is automatically incremented to point to the next instruction in memory, address I plus 4.
So it just naturally moves to the next step.
Yes, it fetches the instruction at I plus 4, executes it, increments the PC again to I plus 8, and so on. This process of executing instructions sequentially from consecutive memory locations is called straight-line sequencing.
Like reading down a recipe, line by line. Now, what are the distinct phases for handling each single instruction in this flow?
Each instruction execution generally breaks down into 2 main phases: instruction, fetch, and instruction execute.
Fetch and execute, okay.
During the fetch phase, the processor gets the instruction. It uses the address in the PC to read the instruction from memory and loads it into the instruction register, IR. Then, usually right after or during the fetch, the PC is incremented to point to the next instruction's address, getting ready for the next cycle.
Fetch the instruction, prepared for the next one. then execute.
Then comes the execute phase. The control unit decodes the instruction that's now sitting in the IR. It figures out what operation to do and what data is needed. Then it generates the control signals to make it happen. Maybe fetching operands from registers or memory, telling the ALU to do its calculation, or telling memory to store a result.
So fetch gets the command, increment points to the next command, execute carries out the current command. That's the core loop.
That's the fundamental cycle, yes. But programs aren't always straight lines, are they? We need loops, we need decisions.
Right. How do we break out of that straight line sequence?
That's where branching comes in. A branch instruction is special. It can change the normal flow. Instead of just letting the PC increment to the next sequential instruction, a branch instruction can load a completely new address into the PC.
Ah, telling it to jump somewhere else in the code.
Exactly. The address loaded by the branch instruction becomes the location where the next instruction fetch will happen. This is how we implement loops, jumping back to repeat a block of code and conditional execution, like if-then-else statements.
Makes sense. So a branch lets the program jump around. Is there just one kind of branch?
No, there are generally two main types, unconditional and conditional.
Okay, unconditional.
An unconditional branch always causes the jump. When the processor executes it, it always loads the specified target address into the PC. Simple as that.
Always jumps. And conditional.
A conditional branch instruction only jumps if a certain condition is true. If the condition is false, the branch does nothing, and the processor just continues to the next instruction in sequence like normal.
So it decides whether to jump or not.
Right. Our source gives an example like branch LOP. This might check if a value in a specific register, say R1, is greater than 0.
Okay.
If R1 is greater than 0, the condition is true, and the processor loads the address labeled LOP into the PC, jumping executing to that point. If R1 is 0 or negative, the condition is false, the branch is ignored, and execution just continues with the instruction immediately following the branch.
And that's how you build loops. Check a counter, and if it's not done, branch back to the start.
Exactly. You perform your loop operations, maybe decrement a counter register, and then use a conditional branch to jump back to the beginning of the loop if the counter is still positive, for example.
Clever. But how does the processor actually know if the condition is true? How does it check if R1 is greater than 0, for instance?
Ah, good question. That involves condition codes or flags.
Exactly.
Yes. Many ALU operations don't just produce a result. They also set or clear specific bits in a special processor register, often called the condition code register or status register. These bits act like flags, recording information about the outcome of the last operation.
What kind of information?
Things like, was the result 0? 0 flag Z. Was the result negative? Negative flag N. Did an addition result in a carryout? Carry flag C. Was there an overflow? Overflow flag V, and so on.
Little indicators about the result.
Exactly. Then, conditional branch instructions can look at the state of these flags. For example, branch 0 might actually check if the N flag is clear, not negative, and the Z flag is clear, not 0. If both are true, the condition is met, and the branch happens.
So the ALU operation sets the stage with flags, and the conditional branch reads those flags to make its decision.
Precisely. It connects the result of computation to the control flow of the program.
Okay, this is really building up a picture. Now let's shift focus slightly to addressing modes. Our source says these are different ways to specify where an operand is located. Why do we need different ways? Isn't just giving the memory address enough?
You'd think so, but different addressing modes offer flexibility and efficiency for different programming tasks, like working with variables, constants, arrays, or pointers. It makes programming easier and can make the resulting code faster or smaller.
Okay, so what are some fundamental modes?
Well, the simplest is probably register mode. The operand is just in one of the processor's registers, like add R1, R2, fast, direct access.
Makes sense. The data's right there.
Then there's absolute or direct mode. Here, the instruction itself contains the actual memory address of the operand, like move LOC R1, where LOC is a specific numeric address.
Straight to a fixed memory spot.
Right. And then there's immediate mode. In this case, the operand isn't in a register or memory location. The operand's value is directly embedded within the instruction itself.
The data is part of the command.
Exactly. Often indicated with a hashtag sign, like add hashtag 200 R1. This means add the constant value 200 to the contents of R1. Very useful for constants. Avoids a memory fetch.
Okay, register, absolute, immediate. What about modes involving indirection? pointers.
Indirection is powerful. In indirect mode, the instruction doesn't give you the operand itself, nor its direct address. Instead, it gives you the address of another location, either a register or a memory spot, which contains the actual address of the operand.
Whoa, okay, an address that points to the real address.
Exactly. We call the final address the effective address, EA. Parentheses are often used to show indirection. So add R1, R2 might mean go to register R1, get the address sorted in R1, then go to that memory address, fetch the data, and add it to R2.
So R1 acts as a pointer.
Precisely. The register, or memory location specified, acts as a pointer to the actual data. This is super useful when you don't know the exact memory address at compile time, or when you need to step through data structures.
I can see that. Like following a treasure map where one clue tells you where the next clue is. What about indexing? Sounds related to arrays.
Very much so. Index mode is great for accessing elements in arrays or lists. The effective address is calculated by taking a base address and adding an offset value stored in a register, the index register.
Base plus offset.
Right. For example, the instruction might look like xray. Here, x is a constant base address. Part of the instruction may be the start of the array, and re is the index register holding the offset. The EA equals x plus ry. Importantly, the content of the index register ry itself isn't usually changed by this addressing mode calculation.
So you can load the start address of an array into X or have it in the instruction and then put 0, 1, 2, etc. into re to access successive elements.
Exactly. Just by changing the value in the index register, you can easily step through the array. Our source also mentions variations, like base with index mode, where the EA is the sum of two registers, re plus RJ. One register holds the base address, the other the index. More dynamic. And even base with index and offset. X plus ry plus RJ adds a fixed offset X to the sum of two registers. Useful for accessing specific fields within elements of an array of structures, for example.
Lots of flexibility there for complex data structures. What's relative addressing?
Relative addressing is a specific kind of index mode where the base address register used is always the program counter, PC.
Using the PC itself.
Yes. The effective address is calculated as EA equals X plus PC, where X is an offset value included in the instruction. This is very common for branch instructions.
It's branches.
Because often you want to jump to a location that's a certain distance relative to the current instruction. Specifying the branch target as PC plus offset makes the code potentially relocatable. You can load the program anywhere in memory, and the relative jumps will still work correctly because they're relative to the PC's current value.
Ah, clever. Makes code more portable. Now, our source also mentions auto-increment and auto-decrement modes. These sound handy for lists.
They are, especially for processing data sequentially, like in loops or stack operations. Auto-increment mode works like this. First, the register specified holds the effective address of the operand. The operand is accessed using that address. Then, after the access, the content of the register is automatically incremented, usually by the size of the operand just accessed.
So it uses the address, then bumps it up ready for the next element.
Exactly. It's often denoted like re plus RD. So move R1 plus R2 would copy the data pointed to by R1 into R2, and then increment R1 by 1 for bytes, 2 for 16-bit words, 4 for 32-bit words, etc.
And auto-decrement, the reverse.
Pretty much. With auto-decrement, often written re, the register re is first decremented by the operand size, and then that new decremented address in re is used as the effective address to access the operand.
Decrement first, then access.
Right. These two modes are super efficient for stepping forward, auto-increment, or backward, auto-decrement, through arrays, or for implementing push and pop operations on a stack using a stack pointer register.
Like built-in pointer arithmetic combined with access. Very neat. Okay, we've covered a lot. Units, operations, memory, instructions, and now all these ways to find the data using addressing modes. Let's dive deeper into the processor itself, a basic processing unit.
Right, back to the heart of it. And at its core, it's that fetch-execute cycle we discussed.
Fetch, increment, execute.
Exactly. Remember the key registers involved, the PC program counter, pointing to the next instruction, and the IR instruction register, holding the current instruction being worked on.
And the three basic steps.
As our source reiterates. 1. Fetch the instruction from the memory location pointed to by the PC, load it into the IR, so IR PC. Double brackets meaning content of the location pointed to by PC.
Got it. Fetch.
2. Increment the PC to point to the next instruction, usually PC plus 4, assuming 4-byte instructions and byte addressing.
The increment.
3. Execute the operations specified by the instruction, now in the IR. This involves decoding it and performing whatever actions are needed, accessing registers, using the ALU, maybe accessing memory again.
Execute. And steps 1 and 2 are the fetch phase. Step 3 onwards is the execute phase.
That's the breakdown. This cycle is the fundamental rhythm of the processor.
Okay. Now, how does the physical structure inside the processor support this cycle? Our source describes a single bus organization first. What's that look like internally?
A single bus organization means that the main components inside the process, the ALU, and all the internal registers, like the general purpose registers R0, R1, etc., plus maybe some temporary ones, are connected using one single shared internal bus.
One pathway for everything inside.
Yes. This internal bus is separate from the external bus that connects the processor to main memory and I/O. To bridge this gap, we have those special registers we met earlier, the MAR, Memory Address Register, and MDR, Memory Data Register.
Right. MAR holds the address for the external bus. MDR holds the data crossing between internal and external.
Exactly. The MAR typically gets its input from the internal bus, but sends its address out onto the external address bus. The MDR is often designed to transfer data in both directions between the internal bus and the external data bus.
So if it's just one internal bus, any transfer register to register, register to ALU, ALU back to register has to happen one at a time.
That's the main characteristic, yes. Only one piece of data can be on that internal bus in any given clock cycle. This can create bottlenecks.
I can see that.
The source also mentions some temporary registers, often included, maybe called YZTMP. These are used internally to hold intermediate values during multi-step operations because you can't always move data directly from source to destination via the ALU in one go on a single bus.
Okay. And something about MUX for the PC increment.
Right. Since incrementing the PC plus 4 is so common, there might be a multiplexer, MUX, at one of the ALU inputs, say input A. This MUX can select either the output of a temporary register, like Y, or a hardwired constant value of 4. This makes the PC increment operation slightly easier to orchestrate.
Okay, a single shared internal highway with some helper registers. What are the really fundamental operations performed using this structure?
Well, our source lists a few key types: transferring data between registers, performing an arithmetic or logic operation using the ALU, and storing the result in a register, fetching data from external memory into a register via MDR, and storing data from a register into external memory via MDR.
How does a simple register transfer work, say R1 to R4?
It would typically take one clock cycle. The control unit would assert the R1 out signal, putting the content of R1 onto the internal bus. Simultaneously, it would assert the R1 in signal, causing register R4 to load the value currently on the bus. So R1 out, R4 and in, done.
Simple enough.
Yeah.
What about an ALU operation like R3, R1 plus R2? You said that takes multiple steps.
On a single bus, yes. It usually takes 3 steps because the ALU needs 2 inputs, but the single bus can only carry one value at a time, and the ALU output also needs the bus.
So step 1.
Step 1. Get the first operand to the ALU input, maybe R1 out, yin. Move R1's content to the temporary Y register, which feeds ALU input A.
Okay. Step 2.
Step 2. Get the second operand to the ALU, perform the operation, and capture the result. Maybe. R2 out, select I, add Zin, put R2 on the bus, select Y as the other input to the ALU, tell the ALU to add, and store the output in temporary register Z.
And step 3.
Step 3. Move the result from Z to the final destination. Zoot. R3 in, put Z's content on the bus, load it into R3. All these actions are precisely timed by the processor clock and orchestrated by the control signals.
Wow, 3 steps for one addition. What about getting data from memory? Say, move R1, R2. Move data from address in R1 to R2.
That involves the external bus too, so it takes even more steps and depends on memory speed.
Walk me through it.
Okay, roughly. 1. Put the address into MR, R1 out, MRN. 2. Initiate the memory RAID. Send read signal, maybe enable MDR input from external bus, MDRNE, and crucially, tell the processor to wait for memory to respond. WMFC, wait for memory function completed.
Waiting for the data.
Right. 3. Once memory signal's done, MFC arrives, and the data is in MDR. Move data from MDR to R2, MD route, R2 in, so at least 3 steps, plus the memory access time itself.
And storing to memory. Move R2, R1. Similar process.
Very similar, just data flows the other way. 1. Put address in MA, R1 out, Marin. 2. Put data in MDR, R2, R2 out, MDN. 3. Initiate memory write. Send write signal, enable MDR output to external bus, MD route, and maybe wait for MFC again, WMFC.
Definitely highlights the sequential nature and the waiting involved with a single bus. Let's trace a whole instruction now. How about add R3, R1, add content of memory add address in R3 to R1.
Okay, this combines memory access and ALU operation. It'll take several steps. Let's break it down.
Step 1. Fetch the instruction itself.
Right. Peek out, MRN, read, select for, add, zin, WMFC. Fetch construction based on PC, start incrementing PC using ALU plus 4, store results in Z, wait for memory.
Okay, fetch started, PC increment started.
Step 2. Finish PC increment, get instruction into IR, zout PC and WMFC, update PC from Z, wait for instruction to arrive in MDR. Then MD route, put instruction to IR. Fetch phase done, now execute.
Step 3. Get the operand address from R3 to ME.
R3L, MRN.
Step 4. Initiate the read for the operand.
Read, MD Rhine, WMFC. Start reading data from memory location pointed to by R3. Wait.
Step 5. While waiting, get the other operand, R1.
Ready. R1 out, yin. Move R1 into temporary register Y, ready for ALU input A.
Step 6. Memory data arrives in MDR. Perform the addition.
MD route, select to add Zen. Put memory data from MDR onto bus for ALU input B, use Y for input A, tell ALU to add, store result in Z.
Step 7. Store the result back into R1.
Zout, R1 in. Move result from Z to R1. And finally, signal the end of execution.
End.
Phew. That's quite a sequence. Maybe 7 or more clock cycles plus memory wait time for one instruction.
Exactly. It really shows the limitations of the single bus approach for complex instructions.
And how would a simple branch instruction work on the single bus? For an unconditional branch, after fetching the instruction, which contains the branch offset, say X, the execute phase would involve 1. Getting the already incremented PC value, which might have been saved in Y during the fetch, onto the bus. 2. Getting the offset X from the IR onto the bus, maybe via a temporary register. 3. Using the ALU to add Y and X. 4. Storing the result, the target branch address, back into the PC. Again, multiple steps using the single bus and ALU.
Okay, clear limitations. This naturally leads to multiple bus organizations. Why go that route?
Speed, performance. The main reason for multiple buses inside the processor is to allow several data transfers to happen in parallel in the same clock cycle.
Break that single bus bottleneck.
Precisely. Reduce the number of steps needed for each instruction by doing more things simultaneously.
What does a typical multiple bus structure look like?
Our source describes a 3-bus structure as a common example. Imagine the register file, all the R0, R1, etc., having multiple ports. Yeah, like multiple connections. Maybe 2 output ports, allowing the contents of 2 different registers to be put onto 2 separate internal buses, say bus A and bus B, at the same time.
Okay, 2 sources read out simultaneously.
Right. And maybe 1 input port allowing data from a 3rd internal bus, say bus C, to be written into a register in the file.
Got it.
The ALU would then be connected to take its 2 inputs directly from bus A and bus B, and its output would go directly onto bus C.
Ah, so operands flow straight from registers to ALU on A and B. Result flows straight from ALU to register file on C.
Exactly. This structure largely eliminates the need for those intermediate temporary registers like Y and Z because the parallel paths handle the data flow much more directly.
That sounds way more efficient.
It is. Plus, you often see other enhancements in these designs, like a dedicated incrementer unit just for the PC.
A separate little adder just for PC plus 4.
Yep. Frees up the main ALU from doing that simple but very frequent task. The main ALU can still calculate other addresses if needed, but the PC increment happens in parallel, often during the memory fetch phase.
Okay. Dedicated hardware for common tasks. Let's see this in action. How would that instruction make up? Add R4, R5, R6, execute on a 3-bus system.
Much faster. Assuming the instruction is already fetched and decoded, which still takes some steps, the actual execution might happen in just 1 clock cycle.
1 cycle how?
In that single cycle, the control unit orchestrates this. 1. Connect R4's output port to bus A. Connect R5's output port to bus B3. Tell the ALU to perform add using inputs from bus A and bus B4. Connect the ALU's output, which appears on bus C, to R6's input port and enable R6 to write.
Read R4, read R5, add them right to R6, all at the same time.
Essentially, yes. All within 1 clock tick, thanks to the parallel data paths provided by the 3 buses and the multi-ported register file.
Wow, that's a huge difference compared to the 3 steps we needed on the single bus just for the ALU operation part.
It's a dramatic improvement. This parallelism is fundamental to how modern processors achieve high performance. More buses allow more work per clock cycle.
Okay, we have covered a massive amount of ground today. Really foundational stuff.
We certainly have.
We unpacked the 5 key functional units: input, output, memory, ALU, control unit. We unpacked the basic fetch increment execute cycle and the role of registers like PC, IR, MAR, MDR.
Yep. Covered memory organization to bits, bytes, words, addresses, endiness, alignment, and the basic read-write operations.
Then we got into instructions, the different notations like RTN and assembly, the 321 address types, straight line sequencing versus branching with condition counts.
And all those addressing modes. Register, absolute, immediate, indirect, indexed, relative, auto, increment, decrement. Lots of ways to specify operands.
And finally, we contrasted the single bus processor organization, seeing how sequential it is, with the multiple bus organization that allows for much more parallelism and speed.
It really builds up from the basic units to how they interact and how internal structure impacts performance.
It really feels like we've gone through a solid prep session for understanding how computers actually work underneath the hood.
Absolutely. Having this foundational knowledge gives you a much deeper appreciation for the complexity, but also the elegance of how these machines execute our programs. You can almost visualize that coordinated dance of signals and data now.
Definitely. And wrapping up this deep dive, it makes you think, doesn't it? How do these fundamental building blocks, the bus structure, the addressing modes available, the way memory is set up, how do they influence the kinds of software we can write or how fast that software runs?
That's a great question to ponder. Those low-level architectural choices really do cast a long shadow, influencing everything from compiler design to operating system behavior, ultimately shaping the capabilities and limitations of the technology we use every day.
It shows that deep connection between the hardware design and the software possibilities. Something for our listeners to chew on.
Hopefully this dive has provided a solid framework. There's always more detail to explore in any of these areas if something particularly caught your interest.
Absolutely. Well, thanks for joining us on the deep dive. Until our next exploration, keep thinking about those fundamentals.